This is a joint collaboration. This work is a joint collaboration between the 35 Live in Paris and the CA-LET in Grenoble. This is a very short outline of what I'm going to present you. While preparing this presentation, I suddenly realized that I should probably anticipate very soon the conclusion. Yes, a fully optical lab on chip, it is feasible, and what I'm going to tell you during the presentation is how we can do that, presenting the main building blocks to fabricate such a technology and to address this kind of device fully integrated on planar substrate. So, sorry, this is let me start with this cartoon showing the main absorption wavelength of a number of different compounds of interest for spectroscopy. As you can see, many compounds have absorption line in the near-infrared region, but the majority of the compounds have the most intense absorption line in the mid-infrared region. And if, for example, you try to compare the absorption in the near-infrared and the mid-infrared for CO2, you can see easily that the intensity is much higher in the mid-infrared region. This means that you can detect those molecules with more reliability and with much more sensitivity. This has a strong impact on many application fields because you can get higher performances. And if you have the possibility of extended sources as it can make available using, for example, QCA lasers, you can have the possibility to detect complex molecules which are not allowed if you do that in the near-infrared region. So let me say something about the first building block of this structure, the sources. For those which are not familiar with the QC laser, this is just a stack of different quantum well, as it can be seen over here in this nice TEM picture. And it is a unipolar device, and when the one electron starts to move from the upper quantum level quantum well structure down to the bottom one, you may have emission of photons, and the energy of those photons are just selected by changing the parameters of the growth we have realized. Typically, QC lasers can span a wavelength range from 3.3 micron up to 15 microns. One single growth can cover, roughly speaking, 100 centimeters minus 1, and when you add a grating structure which allows to select a specific wavelength, you can get a line width of less than 1 centimeter minus 1, which is, or less than 0.1 centimeter minus 1, which is less than the width of a typical gas absorption line as you showed before. The most important thing is that this structure is fully workable in planar technology on one side, and on the other side, you can select the performances of your device just by changing the parameters or the dimension during your fabrication. In particular, which is interesting, is the fact that you can change the period of the grating and changing that way the wavelength, the emission wavelength of the device. And this can be done on different devices, one beside the other. That's actually what has been done by our colleague at 35 Lab. Here you have a series of different lasers fabricated on the same chip. On each of these chip, on each of these devices, the grating period has been slightly changed, and here you have a typical emission pattern of the different lasers, one powered one after the other. Of course, the emission of each laser can be slightly tuned just by changing the current or the temperature of the driving that source, and this allows to have a sort of continuous tuning, moving from one source to the other and powering sequentially these sources. However, if you want to use it for spectroscopic application, it is clear that the output is not usable anymore because it is you have a shift from one source to the other. It might not be important, but in many applications where you need to have an absorption path of centimeters or even meters or even more, it is obvious that it cannot be usable simply putting a lens in front of this series arrays of devices. So you need something to combine the different output. That can be done using waveguides fabricated, mid-infrared waveguides fabricated once again on planar substrate. Here you have what we have fabricated at CELT, which consists on a graded waveguide, silicon germanium waveguide. And as shown over here, we have measured on these structures losses which are state-of-the-art for this kind of devices, lower than 1 dB per centimeter at 4.5 microns, lower than 1.5 dB per centimeter at around 5.6 micron, and lower than 2 dB per centimeter at 7.4 microns. We have used these devices, this technology to fabricate a combiner. Here you have a series of different pictures of the combiner during the fabrication. Of course, we miss here the cladding layer because otherwise we will not be able to see anything. And on the bottom figure, you have the output of the unique output of the combiner with the input of 35 different lasers, powered one after the other, and you can also see absorption of the water that was present during the test of this device. So at the end, we have a device which is a widely tunable QCL source. And nowadays we have a startup company issued from the 35 Lab and the CELT commercializing this device as a product for prototyping and commercialization and fabrication of new type of system. You can contact them if you want to have prototypes of this source. Of course, we have to move forward. For the moment, we are just assembling the two different chips, one in face of the other, in front of the other, and have a sort of matching between the two wave mode into the two waveguides. And the transmission just makes because we are injecting directly into the waveguide. The next step is to try to integrate directly on a silicon substrate the AP layer consisting of the QCL stack, and this is the next challenge for this fabrication. We are now working actively on this part, and we just recently be able to molecular bond the AP layer and remove the support of the indium phosphide wafer supporting the AP layer for the fabrication of the QCL stack. Of course, this is an extremely challenging technology, but we will expect to have a first result of laser fabricated directly on silicon in a few months from now. Moving forward in the chain of the detection, we have been discussing about the multi-lambda sources. We have been discussing about the beam handling. Let me now discuss about the detection. You have seen examples of detection fully integrated on the chip in the previous presentation. This is a way. We chose another way based on photoacoustic detection. Just because photoacoustic detection, beside the different detection mode that you can have, it is particularly suitable to be miniaturized. In particular, it turns out that photoacoustics scale down with the volume of the cell, which is particularly adapted for shrinking down everything on a planar substrate. Of course, the requirement for such a kind of device is to have a cell size compatible with the wafer thickness, because we want to integrate everything on a wafer. To have something which is feasible and not too much complicated, and to have to take into account the fact that downscaling at the given limit may found some limitation due, for example, to the absorption on the different surfaces, or by the fact that the interaction between the light and the gas is not good enough. So to do that, we have defined a series of specific design rules. In particular, we have chosen to stack 3 different layers. One layer including for the realization of the microphone, one layer including the waveguide to bring the light directly inside the photoacoustic sensor, and the third wafer to allow the gas distribution within the miniaturized photoacoustic chamber. One major limitation coming from that is the fact that first of all, we have to deal with rectangular, parallelepiped volume, which usually for photoacoustic we deal with cylindrical type of volumes, and this may cause some problems during the fabrication. And the other very critical point is the fact that we have to match the technology waveguide and with the technology of the fabrication for the fabrication of the microphone. Last but not least, a few words about the specific configuration we have chosen. Here we are using a so-called differential Helmholtz resonator, which allows to be immune of the noise coming from the external. In this case, the light interaction with the gas cause an imbalance, a perfect imbalance between the two cavities. So only the measurement out of phase can be taken into account by the electronics afterwards, while in the sound coming from the external is just seen as a in phase noise, and it is subtracted by the measurement itself. To go more into detail concerning the fabrication of the microphone, here you have a few pictures concerning the type of microphone we have chosen, which is not traditional. It is a beam moving just under the effect of the pressure variation caused inside the microphotoacoustic cell, and the movement is detected by a narrow silicon gauge, 200 by 200 nanometer by 200 nanometer in size, which can be measured and detect the movement by a piezoresistive effect. This is particularly suitable to be integrated in the structure we have seen before. Typical MEMS microphone, as those we have in our cell phones, are not so suitable for this kind of configuration, and it takes too much place to integrate in this part. So we are now fabricating the first prototype of this cell. At the end, it would be something which has a volume in the range of a few nanoliters, and we have done, of course, a number of different modeling to design this cavity, and it turns out that according to our modeling, with 1 milliwatt source and 4 microphones per chamber, we will be able to, the estimated limit of detection for CO2 would be on the order of 0.05 ppm, and for CH4 on the order of 0.5 ppm. The first prototype of this device will come soon, and I hope I will be able to discuss it in the next presentation. So to come back to the summary, I have presented to you the main building block fabrication for the fabrication of a fully integrated optical lab on chip And here you have picture of the 3 different devices. Last, I would like to acknowledge the support of a number of different national and international projects that have supported this activity, and all the colleagues of the Mickael Nanofabrication Facility at CALT and 35 Lab in Paris, and the postdoc and PhD students that have been working with us on this activity. Thank you.